Thank you very much for being here, everyone. I would like to welcome you too. Hopefully this will be a productive workshop. As you can see, I'm going to continue after Matthias's talk with some more practical and also technical things. For one thing, because we have to, if you want to compute anything, implement electronic structure theory in some way, and some of the concepts will show up in this talk. And also, of course, because there will be practical tutorial sessions tomorrow and then going on throughout the rest of the workshop. And some of the concepts I'll introduce here are related to the FHI Ames code, which you'll be using. So I'll also use this talk to introduce things about how we happen to do things. And then there'll be several other talks. I'll point them out throughout the presentation that will say how things could also be done. So this is by no means the only way of doing things. There are many possible ways to get useful results out of electronic structure theory, and those will show up during the workshop. As you can see, I modified my title slightly. I'm calling it Computational Material Science from Scratch, with a subtitle of the nuts and bolts of electronic structure theory. There are way more nuts and bolts than I can cover in this single talk, but I hope to cover some of them. And please ask questions now, later, actually even throughout the talk if you like, and during the workshop. My name, as you may have noticed by now, is Volker Blum. I'm actually in the Department of Mechanical Engineering and Material Science, so an engineering department at Duke University in North Carolina in the US. And that's where we pursue this. A lot of this originated, of course, at the Fritz Haber Institute, where the code also originated. And yeah, we hope to make this useful for a very long time. Matthias showed his graph saying that if you want to get into the field, 1980 is a good time to get into the field. This is true. I made a quick calculation not too long back to see how I was doing, and I can happily see myself finding useful stuff to do in electronic structure theory at least until my retirement and hopefully beyond. So I think we have some future here that we can exploit and make better predictions for new materials. So this is where all this started, and this slide doubles as an acknowledgement to the many people here in the room and elsewhere that contributed to this talk. The actual code development in a narrow sense that I'm involved in started here in the villa of Richard Willstätter on the campus of the Fritz Haber Institute in Berlin. This first floor here is part of the theory department. I moved to Duke University in 2013 to this fine hall here, which is Hudson Hall, or the engineering hall on Duke campus. The people in the group that grew since then, some of them are actually in the audience, contributed quite a lot to what we do. So William Hoon is here. He's organizing, I think, the second tutorial. He's the senior postdoc in the group, basically overseeing everything. Victor Yu is here. He works mainly on something called electronic structure infrastructure, or ELSI, which Karsten pointed out on the first slide already. Garnet Liu is also here, who works on excited states, actually, towards excitonic effects, and then also complex materials that are in the perovskites field, but large organic-inorganic hybrid perovskites with interesting organic functionality, and various other people in the group that have done something over time. But most importantly, as far as my own exposure to code development goes, these 100 people here and these individuals here should be thanked, because this is really the code development of FHI Ames in particular, a multi-center, multi-individual effort, and I think by now we probably have well over 100 developers. I counted them once, who contributed to our Git repository to the code, and this is a growing group and a lot of fun to work with. So thanks to all these people here. Before I start, here is a brief outline of what I'll try to cover. The Kohn-Sham equations, of course, that Matthias introduced are going to be the center. These are three-dimensional partial differential equations. They're the base also if you want to do many-body theory, usually for what we want to do. And we want to solve them for these orbitals here, which give us the density later. So these are functions in three-dimensional space. And these eigenvalues here, perhaps, which are formally just parameters that are introduced as Lagrange parameters, but might double as something useful, or at least can help us calculate the total energy of the entire system later if we augment them with a few other terms. And the whole thing, of course, has to be calculated in a manner that I won't say much about, but I think Oliver Hofmann is going to go into that tomorrow, which is called self-consistent, because these are not linear differential equations, although they look like linear differential equations. They're non-linear in the sense that the solution over here, the psi, enters these potentials here, and you only have a solution that is truly complete if the potentials, electrostatic and exchange correlation potential over here, give you the wave function that will determine the exact same potentials that you started with. So this is an iterative loop that we always have to solve. Anyway, these are the Kohn-Sham equations in a nutshell. There will be a lot more about this, including about the self-consistency loop tomorrow. I won't say very much about it, but we need to solve them somehow, and for this we need some technical concepts. And the most important technical concept in our field is how do we discretize these equations. So I'll speak about basis sets a little bit. You could, of course, try to solve all this in three-dimensional space, and that's all nice and well if you have a lot of time. But in quantum mechanics, we typically deal with sets of basis functions, and that we do too. Integrations and grids on which we do stuff are still going to be important, and every electronic structure code has its own variety of this. I have to talk about this too. Molecules and periodic boundary conditions, so non-periodic versus periodic geometric boundary conditions also play a role. I'll say some words about how to deal with relativity, particularly a little bit about spin-orbit coupling, and then finally about scalability. So it's nice if you have a code that can deal with 10 atoms, and that's fine. But many materials are not just described by a 10-atom unit cell, and molecules not just described by 10 atoms. You want to go to perhaps hundreds or thousands of atoms. You want to do many of these calculations. You want to use a computer that's not just a laptop. This laptop will run the code just fine. I noticed after hacking a few, this is a new laptop in fact, after hacking a few problems away in the libraries I was using. So that's good, but if you have not 4 cores, which this year sports, but 40,000 cores perhaps, you'd still ideally like your code to use those efficiently, so you need to care about scalability. And I'll come to that towards the end of the talk. As I said, and as everyone else so far said, our implementation of all this used for the tutorials is the FHI Ames code. I, of course, have a particular love for this code since I think I wrote the first line. It's an all-electron implementation, so it makes no basic approximations to the potentials we use, to the nuclear potentials. It deals with molecules. It also deals with periodic systems on exactly equal footing, and it can do a bunch of things that will show up throughout this talk. It's the main example in this talk, but as I said, other examples of basis sets and different strategies to address the electronic structure problem will show up in the next few days. So I won't say much. It's going to be a technical talk. I won't say much about dazzling scientific applications, and maybe that's a mistake, because ultimately I'm actually not in this business to write code. Then I probably would have found a different profession. I was interested in the material science and molecular science that we could do, and that's how I got into this field. I just noticed that density functional theory and its various extensions were particularly useful if you pushed them a little. But so in our group, as well as everybody else, we have some scientific goals. I'm using the goals in our own group because I know them best, but they're also representative for some things other people want to do. And then obviously everybody probably has their own motivation to want to do something, but we'd like to cover this with an electronic structure code if we can. So we did, when I arrived at Duke University, find a very fruitful collaboration with a group of Stefan Sauscher, who does atomic force microscopy to characterize nanostructured materials, basically. And one of the materials we were interested in was to characterize samples of graphene on silicon carbide. And what they have in particular is a technique that allows them to use an atomic force microscope. So basically a tip on a surface, not just to scan over the surface and get a topographic image, which you see here on the left, but also by a resonance technique. So they put a resonance frequency on their crystal and look where the mechanical resonances are, to look basically under the surface and see what happens at the atomic scale under their graphene layers. And in fact, something happens there, at least in this sample, which is an oxygen intercalated sample. So somebody intercalated deliberately oxygen and water vapor under this flat layer, which is allegedly graphene, on top here to decouple it from the substrate. And you can see that if you can look under the substrate, you see a lot. What does electronic structure theory have to do with this? Of course, we know the resonance frequencies here quantitatively, so they've measured those with their AFM. And we can make a model of the surface. This is just a toy model showing a silicon dioxide layer underneath 3 layers of graphene on a silicon carbide sample. This is not the actual surface structure, it turns out, in the end, although perhaps for this number 3 it could be plausible. Then you can make an elastic model. You can calculate in 3 dimensions, not just in 1 dimension, elastic constants, put those into a continuum model, and in fact get resonance frequencies that, if you know what the structure is, match the AFM. So you have a fingerprint, a mechanical fingerprint, to figure out what could be underneath the surface or perhaps what it might not be. And this we can do with electronic structure theory, except to do it right. This particular structure model here has to have of the order of 1,300, 1,500, maybe 2,000 atoms, depending on how accurately you do it, because the graphene doesn't quite fit on the silicon carbide underneath, so this forms a large superstructure. And this is something, if you want to, we can try, and of course we want to. Then there is the other problem that is familiar to many in the audience, I think, which is to create new materials with better electronic properties. Our own effort here comes together with a group of David Mitzi at Duke University, who is an expert in thin film solar cell materials. And this is basically about finding materials for photovoltaics that are equally good or better than existing thin film materials, but are in their elemental composition earth abundant, so you have enough of them on Earth, and hopefully non-toxic, so you don't start spreading toxic elements around by implementing an allegedly clean energy technology. David came up with this material here, copper, barium, tin, sulfur selenide, which actually works. So in a prototype solar cell that they have, in the meantime, we've worked on this for 2 years, it gives 5% efficiency for a new solar cell material that's actually pretty good. What we can contribute is we can calculate band structures and try to predict effective masses from this, the actual band gap, and other characteristics that they might be interested in. And for this, we need to use relatively high-level electronic structure methods. So this here is rung 4 of Purdues Ladder that Matthias introduced, a hybrid functional, including some relativistic effects, spin-orbit coupling, but we can do that. Then we're also interested in understanding materials for other purposes. For instance, photo-induced generation of hydrogen, another clean energy technology that if we could make that usable would be highly useful in terms of capturing and harvesting solar energy. We were interested in hydrogen evolution materials with a group of Bettina Lotsch, and here the problem is really that not even the basic structure of the compounds is known. I've just put 3 out here that are particularly popular structure models for this class of materials, and this one in particular is one that's much discussed. It's a so-called graphitic carbon nitride, or C3 and 4. Because it's a 2-dimensional material, it almost looks like graphene. There's many, probably well over 1,000 publications studying the properties of this material. We did some ab initio thermodynamics that Matthias also briefly introduced in his talk to see under which conditions this material is actually stable. And it turns out that according to our ab initio thermodynamics, this material is in fact not stable under any common synthesis conditions. We wrote a paper on this, and this is out now. We'll see whether this changes things, but still there's a large community that believes in this material and will happily plow on and calculate its properties, although if you do a detailed analysis, it's not stable. Of course, this wasn't quite our idea. It was actually our experimental collaborators who pointed out to us that in spite of the literally over 1,000 publications on this material, it was their opinion that common synthesis techniques cannot produce it. And electronic structure theory validated that fact. And then finally, we do some completely different things, molecular spectroscopy in these things. We'd like to be able to look at response properties associated with the nuclei in magnetic fields, nuclear magnetic resonance, or more commonly MRI if your knee is broken and somebody needs to look in there. Magnetic resonance spectroscopy is a useful technique for doing that. There are other things you can do, however. For instance, you can create molecules with long-lived states that are polarized in a magnetic field. The problem of conventional MRI is that you use the protons in your knee to image. but you polarize them in a large magnetic field directly, and you get polarization densities of maybe 10 to the minus 4 to 10 to the minus 6. So our experimental collaborators, whose idea this all is, Thomas Theis and Warren at Duke University, would like to design these molecules, which they call this hyperpolarization. That's actually a larger field in that area. Basically, transfer the natural nuclear polarization of hydrogen to those two here and create polarization densities of 40%, not 10 to the minus 4. And if you can do that, perhaps one day there'll be low field magnetic resonance imaging with probe molecules like this that won't need a big machine to analyze your knee. That would be a radical breakthrough in diagnostics. But you need these molecules here, and to predict what is a good molecule for that kind of application, you need to calculate these parameters, which are quantum mechanical parameters. This, for instance, is the spin-spin coupling of two nuclei, J, and that's something we can do with electronic structure theory, and that's something we're also interested in. There are many more examples of this kind, and we can do them from quantum mechanics. And, well, we could do much more if we can extend the reach of these simulations. So that's what is my main business. I'm interested in tinkering and trying to push out the power of these simulations. And the question is, how can we make this happen? In parts, by continuing to tinker. And as I said, I hope to see interesting stuff in this field emerge until well after my own retirement, and I hope that's a while away. Matthias mentioned this part, and I'll just repeat it because it really is fundamental. The reason we can do this is because we have a theory that's fundamentally sound. That's a very important realization. Fundamentally, we sit on a theory which is quantum mechanics, and that appears to be, for all practical purposes, exact as far as phenomena go that we can produce on our globe unless we work really hard. If we work really hard, we can build a particle collider and find some new physics, but that's tricky beyond the math we know. And so this Dirac equation here, not Schrödinger's equation, appears to be enough for most of physics and chemistry. Dirac summarized this in the quote that Matthias quoted before. Matthias also pointed out this Hamiltonian here, so I'll just repeat this, which is the non-relativistic version of coupling all electrons and nuclei in a single Hamiltonian. Then you have this wave function here, and if you can calculate the wave function, you're actually done. However, this couples all the 10 to the 23 or so parameters in a single crystal, say, that you might want to look at. So this is tricky. All the coordinates are coupled. We can't get around this. It's difficult, in fact, to even ignore the time dependence. You can get around that, but if you want to treat nuclei and electrons explicitly together, then time-dependent formalism seems natural as well, which is, again, difficult. So what to do? Well, first we read the next sentence in Dirac's quote, which Matthias also quoted, the fact that things are a little bit computationally complex and perhaps not exactly soluble. That's great. And let's develop practical approximations. Well, this is what we'll do in this talk, and this is what I'll confine myself to. The Born-Oppenheim approximation is a very interesting one. It's also on here for that reason. In fact, my empirical analysis says that even if you want to go beyond the Born-Oppenheim approximation, most of the tractable solutions that people actually have start with the Born-Oppenheim approximation and then expand from there. At least in chemistry, that's been an active field for a while. So we're going to take the electronic subproblem after the Born-Oppenheim approximation, and this is all I'll talk about in this talk because that's enough in and of itself. So we'll solve this Hamiltonian here, the electronic Hamiltonian. We'll actually do density functional theory, obviously, instead of taking this Coulomb interaction between the electrons outright. And this is the Schrödinger equation. H phi, in this case, equals E phi, is what we'll focus on, hoping that we can solve at least that. Let's see how far we'll get. This picks up another piece from the earlier talk. At some point, those talks will diverge. Electronic structure theory, as we need to cover it in a code right now, roughly goes like this. There's quantum chemistry, which starts in the late 1940s in a practical sense, early 1950s, and which basically takes the wave function and refines it outrightly, successively, ideally for the ground state by using a variational principle. So you minimize this energy until hopefully you're close enough to the solution, and then you have your practical solution. This works very well However, with constraints, size constraints, computer time constraints, and those high accuracy quantum chemical methods are extremely valuable as benchmark methods, but they don't go out and practice beyond several tens of atoms, perhaps several hundreds. We don't want to move them, but that's unfortunately where this route at this point ends. So there's the alternative route of density functional theory, where you rewrite the total energy as a functional of the density. And then with the Kohn-Sham equations, these three terms here, the kinetic energy, the potential, the external potential, and the electrostatic potential, are things that we can actually calculate. They're simple to calculate, and everything that's complicated is hidden in the exchange correlation functional over here. And you've seen this here before, except I call it Purdues Ladder. So there's another name for Jacob's ladder or Purdues dream. These rungs here, as Matthias already introduced, correspond to different levels of the approximation. John Purdue coined this hierarchy in 2001, I think. Hopefully the accuracy increases as we go up. For sure the cost increases as we go up the rungs of the ladder. So at least we should understand what the benefit is of each of these rungs when we apply them, to apply them correctly. So we have the local density approximation, the lowest rung, generalized gradient approximations which rely on the gradients of the density. Then this large unfinished field of meta generalized gradient approximations, which basically introduces second derivatives into the mix. And then a slight deviation from the true path of Kohn-Sham, the hybrid functionals that mix in some form of non-local exchange, but that apparently bring a piece of the right physics back to repair the exchange correlation functional, at least in terms of predicting things like band gaps. Not the full physics, however. That happens at the fifth rung here, which is many-body theory, such as the random phase approximation. I added GW, so the prediction of electronic excitations to the mix. This will show up later during this workshop. And other diagrammatic approximations that one can make, like this second-order screened exchange. But the point is that at some point we'll come full circle, hopefully, and get back to many-body theory in the quantum chemical sense and converge to the same result if we were to pursue this ladder. The other point that I also have here is that these four rungs here don't have van der Waals interactions, so you do have to worry about treating them in the right way. And that's not always trivial, because, for instance, the local density approximation here may already have extra interactions that shouldn't be there, that intermix with the van der Waals interactions that you have in a pure weakly interacting picture of molecules that are separated in space. So this is a little bit tricky, and ongoing research to be covered by Alex Kachenko tomorrow. So what we wanted to do with our own electronic structure code is basically cover the full spectrum of materials that are reasonably relevant. So basically very light elements to very heavy elements in the range of 80, perhaps 90 or 100 is what we'd like to be able to cover. We wanted one method that would be able to cover all of this with reasonable efficiency and seamlessly, something that would cover periodic and non-periodic systems, the traditional line of division between condensed matter physics and quantum chemistry. We wanted something that allows us to implement the hierarchy of all these methods that you saw on the slide before, not just density functional theory, but also the perturbation methods beyond, something that's all electron, that's scalable with respect to system size and number of CPUs if you have a large enough computer. And finally, something that's efficient, but not efficient at the price of sacrificing accuracy. So this is a problem in general. You can always gain efficiency by making your numerical approximation a little less accurate, and very often that will work. But it would be nice to be able to check. So in my early days in this field, before, in fact, this code came around, FHIMs, I checked occasionally and I found something, which was unfortunate. So one of the things that I was interested in was having a tool that even if I made an approximation for the sake of efficiency somewhere, I would be able to go back and check for the final result in the same code. What would be the result without that approximation? On a numerical level, this is a hard goal to achieve, to get the full numerical result for the eventual final large, perhaps, structure that you want to deal with in your calculation. But that's something we wanted to accomplish, and it's in fact possible if you work hard enough. So the key problem, as I said before, of discretizing these Kohn-Sham equations is finding a good representation that's numerically efficient in terms of a basis set. Once you have that, you can rewrite the orbitals up here in terms of a linear combination of basis functions. Someone has to tell you what these phi's are Thankfully, somebody told me. Once you have that, you can do these integrals here over the Cohen-Sham equations up here, so Hamiltonian integrals, and this thing here, which is called an overlap integral. And the whole thing breaks down to matrix algebra. And this is, you'd think, packaged in libraries that are general in linear algebra, and so you can access them as standard software on a computer and solve this eigenvalue problem here. And then perhaps you have to deal with a small problem of self-consistency in this equation, but at least you can solve this here as a matrix problem. And then you can look at what are the options, and there are many good options, and all of them will show up, or many of them will show up in this talk. The ones that I mentioned here on the slide will. So plane waves is a natural prescription in solid-state theory if you're willing to put up with the fact that you might not be able to deal with the core electrons directly, so you need to parameterize them out in a kind of pseudopotential or perhaps projector-augmented plane wave. But this is standard technology and has been done for many years. Gaussian-type orbitals are the competition from the quantum chemistry community, and this worked in the 1950s. So this is actually, from a computational point of view, really an accomplishment. The reason is that this form of basis functions is very easy to handle in terms of analytical integrals, and so you can get at not just 2-center, but 3 or 4-center integrals rather efficiently, which you need for the actual 2-electron Coulomb operator for real correlated methods, so to treat the Coulomb interaction between electrons outright. And that, in the 50s for sure, was only possible with Gaussians on a reasonable scale, and that's why they continue to be popular to this day. There are, however, many other important methods that work and are relevant for very specific reasons of their own. Augmented plane waves are developed here in Berlin at the Humboldt University very strongly, and this is still the gold standard if you want to assess the accuracy of density functional calculations for solids, for instance. Essentially, if you don't know what to do, you go to your favorite LAPW code and see whether you get the same result as with another code, and this is usually reassuring. This comes from Slater in 1937 at its base, though, so it's also an old prescription, and it's incredibly valuable as a benchmark tool and for many more things these days. There are wavelets, which are also, if you push them hard, can give you benchmark accuracy from but these are really applied mathematics tools. So they're borrowed from the applied math community, like finite elements that have been around for a long time. Our choice is this thing here, which is so-called numeric atom-centered functions. I'll talk about these in a moment. But they have the simple form here, which are basically functions that are centered at an atom. So this R here is attached to an atomic coordinate. The angular contribution around the atom is modeled by an angular momentum function, and the radial function is a radial function that in principle could be anything in shape. And this enables you to place in core functions of the free atom, which basically capture the core behavior also in bonded structures, but also to place targeted functions to capture the valence regime and get at total energies rather efficiently in density functional theory. So this is our choice, but the point is that all these other methods will show up as well. So Xavier Gons, I think, will talk about plane waves on Wednesday of the Abinet project. Igor Ying Zhang, one of the co-organizers, will talk about Gaussian-type methods, I think, on Thursday. Pasquale, I think, will talk about LAPW on Wednesday. And then Stefan Gödecker next week will talk about wavelet methods, I believe, which also have some very interesting properties to them. I'll come to that in a few seconds. Now back to the numeric atom-centered functions that we'll use. Again, they look like this. And the key point, we didn't invent them. There are many other implementations, both all-electron and pseudopotential, that use these. We were most inspired and influenced by Bernardelli's implementation, DMOL, when we started our own code. But the key point is that these radial functions here are flexible in their shape. So you have to evaluate them in a numerical way, for instance, by a spline. But this can be done, and once you have suitable integration techniques, you can use them and use them for science. In practice, we restrict this anything you like a little bit and calculate our own radial functions from a one-dimensional Schrödinger equation like this here, except that this here is, again, something that is anything you like. It could be a free atom-like potential, but it could also be a hydrogen-like potential, which Slater essentially started as Slater-type orbitals in the 1930s already too. So this is not a new recipe, and you could introduce all sorts of other basis functions if you wanted in the same recipe, but just varying this potential. The key point is that you can strictly localize these functions by adding a cutoff potential to the generating equation here, and this pushes the radial function smoothly to 0 at a certain radius. This is a radius that can be fairly large, so in our cases this is typically 5 or 6 angstroms, but can be more, so it's a convergible parameter. It's really just there to not to shape the basis function, but to cut off tails that otherwise decay relatively slowly. And once you cut off these numerical tails, you get functions that are strictly confined to a certain domain in space. And this means that the expensive steps in the calculations, the ones with a high prefactor for smaller systems, like integrations or density updates, can be essentially rewritten in a fashion that scales as order n, so linearly with system size n in some way. And this is the base of why this method actually has any chance of dealing with large systems efficiently. So this is very useful as a property, and we use this all the time in practice. But the key point, of course, is that if you want basis sets like this, the choice of efficient and of enough radial functions is obviously one that you have to make. In our case, we actually have a basis set library, and you'll find them with the FHI-Ames code as used in the tutorials here. We have a basis set library for all elements, from few basis functions for fast qualitative calculations. If you want up to very large basis sets that are there for benchmark calculations, but certainly not for production, but can produce milli-electron volt converged total energies for density functionals of the semi-local kind anyway, and hybrid density functionals. So this really is an efficient and accurate approach. These functions took me about a year of my life to develop, but there is actually a systematic prescription in which one can derive them for semi-local DFT anyway. So ultimately what you end up with, this is an example for hydrogen, carbon, oxygen, gold, you end up with a number of prescriptions that basically for each element parameterize different versions of this equation here. So choose this potential basically in some way, this generating potential. So for instance, if you go to the hydrogen atom, you'll find the free atom 1s function as what is called the minimal basis. Same for carbon and oxygen. They'll have their own valence and core functions as the so-called minimal basis. That's the free atom solution. But then you add functions. So for instance, the next function that comes here for hydrogen is a 2s-like hydrogen function without any other generating potential, but for a nucleus of charge 2.1. This basically scales the shape of the function to make it broader or make it sharper. And the numbers here emerged from an automated algorithm that was used to optimize the radial function shapes that would minimize the total energy fastest for a very simple set of test systems, which were symmetric dimers. So for instance, hydrogen and hydrogen at different distances of the bond. And that turned out to be sufficient to generate basis sets that held up pretty well. So if you like, you can use this minimal basis set prescription. That won't work very well. I'll show you in a second. But you can use this tier 1 here for hydrogen or for carbon. And it turns out that those few radial functions that you add to the basis set already produce surprisingly reasonable results. This is not just our observation. This is actually the key observation also of quantum chemistry, who have very similar basis sets, although produced by different insights or intuition on the Gaussian side of things. If you want something more accurate, you can add in this tier 2 and so on. In the input files to the code, this is basically commenting in lines or commenting them out that are pre-written in an input file. So you can steer this in a relatively simple way. In practice, what this means is you get convergence like this. This is the calculation of the bond energy between two water molecules, so the simplest possible hydrogen bond. That's something that these basis sets were certainly not parameterized for at all. So this is really, as far as these basis sets are concerned, a prediction. We can calculate, of course, the exact result at the PBE level of density functional theory to a very high accuracy if we want to. So we know the limit we should achieve if we have a basis set that's good enough. You can see that if you use this minimal basis, so just the atomic functions, you're way off. So this really wouldn't work. Well, with this tier 1, or our light settings, you're about 10% off the hydrogen bond energy, but it turns out that geometries are already remarkably good at this level of theory. If you go to tier 2, which for light elements are the tight settings in the FHI-Ames code, you're basically there by approximately 5 millielectron volts. And if you really want to go beyond that, you can add in further basis functions, and this will get you to the numerically converged result. The question is, how much do you need? But as a prescription, this turned out to be sound. Now, I could give you 500,000, 10,000 more examples that this would work in detail. Thankfully, last year, a science paper appeared by Stéphane Cottenier, who's also going to speak here next week, led by Kurt Lejagre, but also 68 co-authors, that I think for the first time really got together a large part of the condensed matter electronic structure community to compare the results of the different codes quantitatively. So they used the simplest Drosophila, the one Matthias showed in his talk a few minutes ago, which is the E versus V curve, so the energy versus volume curve or equation of state of solids, except they didn't just do that for silicon, which everybody has tried at some point in their life. They parameterize these accurately, calculate these accurately using LEPW, so augmented plane wave methods for 71 elemental solids, and then got co-authors from 15 different codes, all electron or pseudopotential codes, and 40 different pseudopotential sets together to compare the differences in the equations of states, and they even normalized the bottom of this curve here. So the absolute scale of the curve didn't matter, just the shape of the curve, and they call this the delta test. And thankfully for FHR Ames, these tests were not carried out directly by us. They were carried out by Marcin Dulac, who at the time was a postdoc at Danish Technical University in Copenhagen. And he did contact me at some point, but most of what he did, he actually did from the manual. He contacted me about a few tricky cases, like how to initialize antiferromagnetic chromium or so, but that was basically it. Otherwise, he did this by himself, and thankfully, the code held up with its basis sets where it was expected. That's why we wrote the thing in the first place, to be accurate, which is among the other all-electron codes. So here's the Wien2K LEPW code. Here's the exciting code that's developed in Berlin. The ELK code is down here, 0.3. For some reason, it moved down here. But anyway, we were within numerical errors of the other codes, and that was something that was quite happy to see. The pseudopotential codes like Quantum Espresso, VASP with various prescriptions are also here. However, the science paper has a small time evolution that I'm not showing, and this delta test benchmark really improved things quite a lot also for these codes because they're earlier iterations and they're further down in the list. So this systematic testing actually accomplished something. We did then, unexpectedly last year, get drafted into a different test, which tested not just the relative shape of curves such as this, but actually the absolute total energy accuracy that we could achieve with our basis sets for molecular systems, where that is possible. So I had been in this business of numeric atom-centered orbitals for many years because this was, as far as I'm concerned, the one method that I was aware of that could give us a very low total energy because it's accurate towards the nucleus, but also scale out to very large systems in a relatively simple way because of the relative simplicity of the basis functions. Now, other contenders have also been out there, in particular Luca Frediani here and then Stig Rune Jensen are working on a code based on wavelets. So this is basically a systematically refinable basis in real space. It comes from applied math. And it turns out if you push this prescription hard, you can also converge the total energies of multi-atom systems. They did this for 211 small molecules in the range of around a few to 10 to perhaps in the largest case, I guess 20 atoms or so. And they put out a benchmark set of converged total energies for various functionals, local density approximation, generalized gradient approximations, and hybrid density functionals, and compared various other methods against them. So this is this elephant in the room paper that I'm showing here, and they managed to get the elephant into the table of contents image. I won't talk very much more about this. I'll just say that as far as our own basis sets went, this worked quite well. So this is a comparison of total energy errors here from the paper for the various basis sets that you'll see in FHR Ames later, which is here labeled as light, tight, and then a tier 2, which is the second tier of radial functions, and then a tier 4, which is a much larger prescription for benchmark purposes, but also there in the files you have. And you see that thankfully this goes down on a logarithmic scale from maybe 10 kilocalories per mole for light settings. And light settings are tricky because they're supposed to be light, so you don't want to push them to high accuracy, otherwise you get tight, which is somewhere near 0.3 kcal per molecule in this case here. Tier 2 goes down, and if you want to be really accurate, you can go to tier 4 and you get that total energy accuracy out for the functional. So this was gratifying to see because the methods were completely different in their origin, yet get basically the same results. This is a set of standard Gaussian type orbitals compared against them, and these are Dunning basis sets, for those who know what that is, which is a systematic prescription that is not optimized for density functional theory. That's important to remember. If you optimize for density functional theory, you might get something better. But you can see that these are a factor of 10 roughly off in their accuracy if you try to converge DFT total energies with those, because they don't get the behavior near the nucleus right, in essence. And of course, you can then do a study of your own to find out which Gaussian basis set perhaps performs better, because there are some that perform better. But for us, this was quite nice to see. This carries over to atomization energies and to some extent to density properties like the dipole moment. So this was very useful. And then finally, so these are the tight settings, just to show again that we're going to use in this set of tutorials here. And then Will Hoon, who's probably somewhere in the audience, although I didn't see him right now, went and did a similar test compared to the Wien2K APW code, where he compared band structures. And this is just a root mean square error in electron volts here. So this is 50 millielectron volts, this 0.05 mark here. Comparing band structures for 103 compounds, I think, in the end, between different compounds. So elemental structures, compound semiconductors, ionic compounds, and covered 69 elements and showed that basically the same accuracy will also hold for band structures if you use the same principle of underlying approximation. So this is for so-called scalar relativistic theory, and I'll come back to that towards the later part of the talk, if I can. So we have this accuracy, so we can do something. Unfortunately, this brings us to the numerically tricky bits. We have basis functions, and somebody needs to write an integrator. Well, we need to solve integrals like this, which sandwich the Hamiltonian between different basis functions. We do need to update the electron density, which does cost time if you want to evaluate splines to do so. You need electrostatics, and if electrostatics is not accurate, any electronic structure code will go haywire, so good thing we can do this. We need to deal with relativity, which is why Dirac was on that first slide, not Schrödinger, because the Schrödinger equation will at some point progressively break down. It'll work perhaps till calcium. Maybe if you're lucky, it'll work to gallium arsenide if you look at it with loving eyes. But for lead or gold, the Schrödinger equation in the non-relativistic form will not be particularly helpful. You want something that approximates the effects of the Dirac equation. So we need to deal with this. And then finally, it turns out that this eigenvalue problem, which I downplayed before, so this matrix algebra problem, scales as order n cubed if you want to solve it, order n cubed with number of electrons, at least if you want to solve it for the front door. And since everything else scales below that, this is going to become the computational bottleneck. So you can do 1,000 atoms in 10 minutes, say, but this means for 10,000 atoms, you'll need 10,000 minutes, so a factor of 1,000 more for a factor of 10 in system size. And this is evidently not scalable, so you might want to do something better, and we'll come to that later. These two things here, periodic systems and the Coulomb operator, I think Sergei Levchenko is going to talk about at length on Wednesday, so I'll leave that mostly up to him and focus on these other aspects here. Before I do that, though, stretch. Very good. Great. It's nice and warm in here. It's very cozy. I have a lot of experience singing lullabies for my kids, so I'm happy to see that everybody's still stretching. The people who are really asleep would not have stretched, so every one of you did. Thank you very much. Any questions, anyone? Yes?
I have two questions. The first is how to decide the detailed form of the
How do you decide the shapes of the basis functions? I didn't say much in this talk about this, but you saw the parameters, of course, that somehow appear magically there. And this was actually work. So what I did was I did not want to take this decision myself. I wanted the computer to take it for me in a way that would hopefully give reasonable results to be tested. So in the meantime, we did a lot of tests, and they held up, interestingly enough. But the decision was this. I defined a large pool of radial function shapes. So all sorts of hydrogen-like radial functions, for instance, 1s, 2s, 2p, 3s, 3p, 3d, and so on, with a range of effective nuclear charges. So nucleus 0.1 to nucleus, I don't know, 50, 60 for the heavier elements, maybe 80. And just let a minimization algorithm pick out of this large pool a basis function that would minimize the total energy the most. So it starts with a minimal basis set, and then run through a large pool of it, and for a dimer, run through a large pool of additional basis functions, and find the radial function that would minimize the total energy the most. Add this to the pool, and start again, run through the entire to the basis set, run again through the entire pool, and so on. So it was a completely, eventually automated procedure that required very little intervention by hand. I say very little because some things were too cheap to not do. Occasionally, this prescription for the heavier elements would leave out the finding of an S function in favor of finding a G function, say. An S function, however, is just, it's L equals 0. It's just one radial, one basis function. A G function is 9 basis functions. So there are some S functions in the higher tiers that were there because I decided that we should find an S function first. But except for stuff like this, which was really not much in practice, the prescription worked automatically. And interestingly, it taught me some stuff that I would not have noticed. Some stuff should have been obvious in retrospect. For instance, if you want to go to the lanthanides, who's done calculations on lanthanides before? One. Not bad. Exactly, that was me too. I had not done calculations for lanthanides. Of course, you should know, as every chemist should know, or physicist like myself, that a lanthanide wants F and D type radial functions to choose from, because the electrons and the light ones anyway could fall into a D shell or they could fall into an F shell. So that prescription told me this. Zinc, for instance, happens to have a full D shell, but no P electrons. So there was no P shell in the valence. Now, I would have missed this, but my prescription told me that actually I should add a P shell first, and then very soon another one from a basis set to be useful. Maybe somebody else would have noticed it by finding out that my zinc prescription would have given garbage, but this automated search did it for me before there was any garbage. So it actually worked quite well. A lot of these little things that you know by chemical intuition, and later you think, oh, this is exactly what it should have done. It did automatically for me. And so that's how the parameters came about. Basically, letting the computer search for the basis functions that were optimal for a given set of inputs. Yeah. Yes?
Can you tell me more about this elephant?
Say again?
About this elephant which is in the room.
I could, although I'm not sure I will have much time for this. What specifically would you like to know, the elephant?
Well, an elephant in the room means a terrible thing that no one will discuss. A huge problem which is not acknowledged by anybody. So maybe you could tell me what is this problem?
The problem is the basis set itself. So if you want to have an accurate calculation, and your basis set is not systematically convergible or sits on an approximation that you can't undo, you might do a calculation that looks perfectly normal from a numerical point of view, but it might give you the wrong result. So in many cases, this won't happen. But if you use a basis set that's very small, because you didn't have the money to do more, and try to calculate, say, a work function of a surface where you need the tails of the radial functions into the vacuum to be represented accurately, you'll get the wrong work function. If you can't undo this approximation, not so good. So you might get a lot of results that are half good because you use a basis set that is not great. But converging a basis set absolutely for large structures is very difficult. So getting absolute convergence in terms of total energy out securely is a difficult exercise. So these wavelet people can actually do it, which is impressive. Yeah. We try, of course, as well. So it seems to work. But it's not something that's obvious that you can do this. Most of the calculations out there were not done with a basis set that you can converge absolutely.
Wasn't there something to the effect that results have actually been getting worse over the last few years?
Repeat?
Wasn't there something in this paper to the effect that results have, for some metric, have actually got worse over the last few years?
For some metric?
Yes, so people design a basis set for energy, and then they find that it fails for something else.
I'm certain there are many basis set studies. This particular one, I'm not sure. What this wavelet study said basically was that you can converge with that method the basis set to microhartrees, which is hard to do, and then you can use it as a reference method. And this is independent of the density functional method you put on top. So I think that's the strength of the wavelets, that it's not dependent on the functional underneath. Yeah. We also, implicitly, because we choose the minimal basis for free atoms, we take note of the functional for which we actually work. So our radial functions, the atomic radial functions for PBE, DFT PBE are going to be PBE. For LDA, they're going to be LDA. And this helps in terms of basis set convergence, if you mean that. Anyway. Oh, there are more comments.
Talking about the rationalization for including the dipole.
Say again?
The rationalization for including the dipole
was to include something, that the rationale to include the dipole moment was to include something that was directly a property of the density,
yes,
not just the energy. So that was tested in that paper as well.
Yes.
Yeah. All right. Very good. So I shortened my time, I think. I started a few minutes late, though. But I shortened my time for the technical details. I'll say them briefly as I can, just to say that they exist. Because this is something you don't typically think about in electronic structure code. But then, once you think about them, the question is what you do. So for instance, how do you integrate? You will have integrals like this. You can actually take a continuous integral and convert it into a pointwise integral with integration weights on every point. So you can discretize. But the question is, where do you choose these points? And with an all-electron method, if you try to do this with an even space grid, this will not work. You saw the wavelet example that does hierarchical grids, in a sense, and that's why they can get the accuracy they can get. We don't want to use that kind of grid in this particular code, because this would be very heavy in terms of the expense. Thankfully, people in the quantum chemistry community, Becke, Delhi, and others, pioneered a set of methods for us that enable you to use atom-centered grids with shells that become denser as you go to the nucleus, and that overlap between the atoms with a prescription that allows you to still get these radial weights. And once you have that, you can have a dense grid near the nucleus, you can have a sparse grid further out, and the grids will move with the atoms, but they're naturally suited to the molecular problem you want to do, and this solves the integration problem for us. But the grids we use are not even spaced. That's the message. And in no quantum chemistry code also that does density functional theory, all electron, will these grids be even spaced. How do we get these integration weights? That's a little bit more tricky, but it's actually a relatively standard transformation, also due to the same people, Becke and Delhi and others that I mentioned just now, which basically says, we want something that turns this integral into a sum, and we can do this by inventing a set of functions at each atom that sum up to 1 everywhere in space, but that are peaked individually at individual atoms. And then once you insert the sum, which sums up to 1, you don't do any damage here. And you can define such a function by defining a weight function and normalizing it. In practice, this looks like this. This is taken from the PhD thesis of Jörg Behler at Fritz Haber Institute, in fact, many years ago. But in practice, you have a function, a weight function that looks like this. You put it into this formula, and you get a partition function that looks like that. It's 1 near the atom that it wants to integrate. It's 0 near the other atoms. And if you insert it here in that way, you get integration weights that integrate each atom only near its own nucleus. 5 minutes? We'll see. All right. That's how we can do this. And this allows us to use integration grids on these shells here. So we have to distribute integration points in angular space out here that are relatively sparse compared to what you would need to do if you didn't have this kind of integration. So these grids come pre-tabulated in the form of something called Lebedev grids on each of these radial shells. 194 points, 302 points, 434 points, and so on. And you can see that the integration error of something like this peptide here with 203 atoms converges rather rapidly with the number of integration points on these shells, which means that the integrals are a controlled problem. And of course, you can increase your integration accuracy to however large you want, so this is a convertible parameter. You can use the same trick for electrostatics. That's also important. Without good electrostatics, we wouldn't get anywhere. Thankfully, we're dealing with atoms, so everything is atom-centered. We can again use this partitioning of unity trick, as it's called, just insert it in front of the density. After this, you have a sum over atom-shaped density pieces. You can transform these into angular momentum functions. You can then solve all these one-dimensional angular momentum radial functions, classically Jackson electrostatics. So this is really textbook electrostatics, into potentials, and then you sum up all the individual potentials for the individual angular momentum components and get the full electrostatic potential out. And this works accurately in practice. So that's what we do for electrostatics. And you'll see that there is an L02 parameter, an angular momentum parameter. And thankfully, the expansion order you need is low. So these are, again, total energies and energy differences for large molecules in different configurations, an alpha helical peptide molecule, an extended peptide molecule here versus one another. And you can see that at L equals 6, this is essentially absolutely converged. But if you're interested in energy differences, the convergence sets in much earlier. So that's something that's also convergible, and that gives you practical access to electrostatics. This brings us to relativity. Carsten tells me 5 minutes, so I'll cut the relativity relatively short. Just to say that so far, everything I talked about implicitly was scalar relativistic. And if you look at the band structure, so this is an energy band structure of gallium arsenide, the Kohn-Sham eigenvalues, and look at the green lines, those are the scalar relativistic bands. It's well known in semiconductor physics that things don't look like these green lines. In fact, there's a splitting here, and the bands look slightly different at the valence band maximum, and that's due to relativistic effects. So the splitting here is relatively small, but it's still noticeable, even for relatively light elements like gallium and arsenic, 31 and 33. The splitting is still relatively noticeable compared to the effect of, say, the density functional. So the PBE functional, which gives a wrong band gap way too small, gives this band gap here. HSE gives a much better band gap, the screen hybrid functional, which will show up later during this course. But you can see that the spin-orbit splitting is still not negligible, and it's a key parameter relevant for the transport properties of these materials, and that's for light elements. In practice, here are the light elements. They're much heavier elements. Lead, for instance, has an atomic weight of 82. So here relativistic effects are clearly no longer negligible. If you tried lead, the electronic structure of lead without including any relativity at all, the results would be outrightly wrong unless by sheer luck. So that we cannot do. We need to deal with relativity. And how do we do this? There are essentially two levels of relativity that we do typically. One is called scalar relativistic, which is what most codes do, and for chemical properties, bonding and so on. This is actually a very general and applicable level of theory for calculations. The other one, spin-orbit coupling, comes on top. In the interest of time, I'll cut it relatively short in this case here, but how do we get there? This is Schrödinger's equation again, rewritten in a slightly different form, and the key point is that the wave function here is one component. There's one Hamiltonian for each state, for all states, and we can solve this as an eigenvalue equation. But it's a second order equation, so the momentum operator here is a Laplace operator. In fact, we should be solving this equation, which is a 4-component equation. You only see 2 because this phi here itself has 2 components, and this chi here also has 2 components. And so this here is a 4x4 matrix, which, by the way, is a first order Hamiltonian, not second order. And this is the equation that we should be solving in a relativistically correct or better theory. So this is the Dirac equation. Why don't we do this? Well, we could, but there are a few numerical trickeries associated with it. There are negative eigenvalues in the game. But by and large, it's just expensive to do so, to quadruple the numerical effort. And so what many people do is to rewrite the equation. We can do this. We can solve, these are linear equations, nothing else. We can solve the lower row here for the chi, which is going to turn out to be called the small component. Insert it in the upper row and get an equation that only includes phi. So this is what this equation looks like. Sorry about all the numbers. But basically, at this point, the whole thing is second order because there's a momentum operator here and a momentum operator here. And these sigmas also hang around, which are the so-called Pauli matrices, also a vector. So this is an equation that's close to what describes electrons correctly, except for a few annoying features that we'd have to get rid of. One approximation that we've made is we've lost the norm. We no longer have chi in this equation. So if we solve this equation on its own, we won't get normalized wave functions here. But that's an approximation many people take into account. The second thing is that these matrices here hang around, and a common first step to get to scalar relativity is to simply ignore them and you solve the equation without them. And then we still have the problem that the eigenvalue appears explicitly on both sides of the equation. So it's no longer a linear eigenproblem even formally. We have to solve that. There are ways to do this. In the interest of time, I'll go over them relatively quickly. LAPW and other high accuracy all-electron methods often can be run in a way to treat different regions of space differently. So for instance, you could solve this equation or even this equation here near the nucleus, where it turns out relativity matters. So very close to the nucleus, the potential is very deep, electrons are fast, and that's where relativistic effects are strongest. Or you could use an approximate treatment of this Hamiltonian, except the question is what approximation? And for bonding and valence properties, it turns out that it's an appealing approximation to say this energy here is way lower than the rest mass of the electron, mc squared. C squared is the speed of light. So that's a typically large mass compared to chemical energies of a few electron volts. So why not just leave it away? This is known as zero-order regular approximation, or ZORA. And as written, it's basically useless because it destroyed a property of the Schrödinger equation that we usually have, which is that everything depends on not the absolute level of the energy, but of the potential here, but on the difference between energy and potential, E minus V. This is implicit here on both sides, but here we've destroyed this, and this causes problems. So if you try ZORA directly, this is FHR Ames versus V into K, an all-electron code for the gold dimer binding energy curve. Non-relativistically, they basically agree, except the result is totally wrong. The correct relativistic result is here, but an implementation of this straight ZORA gets you far away. But it's a step in the right direction because the fact that this eigenvalue here is small is in fact correct. It's this potential here, let me go back, this potential here that causes the problem because it can shift as a function of the structure you're looking at. And so it turns out that one appealing way to fix this is to fix this potential here also in a way that has the right shape. So the free atom potential, for instance, and we call this atomic ZORA. We have a few other methods that we played with over the years in the code, but this atomic ZORA holds up surprisingly well. It has no gauge invariance problem, so this problem of the shifting origin, the E minus V, has disappeared because we fixed the V here. The shape of this operator is in fact phenomenologically correct. It gives accurate energy differences. We've tested this many times. It's in these benchmark papers here that I talked about before. And it also gives accurate scalar relativistic valence and conduction band energies. We tested this. And this is basically because the E that we left away over here really is small compared to the speed of light. So the core levels from this method themselves will not be reliable, but the valence levels are. And this is often what you need, pretty much in 99% of the cases, what you want for a calculation of structure or chemical properties. And for the gold dimer, this basically brings us back on top of the correct relativistic curve. This is the short version I said. So the longer version would have been to look at these Pauli matrices here in detail. Will Hoon in our group at Duke did this. Bring spin-orbit coupling back into the game. But then you have to couple the two channels, really, of this large component explicitly in the relativistic equation. Once you do this, you notice that you have a scalar relativistic term over here, which I talked about before, after rewriting this a little bit, that you can treat, for instance, with atomic ZORA. This term here you could treat with different methods. The traditional spin-orbit coupling operator from semiconductor physics is this here, which is already a set of approximations because there's a Taylor approximation involved in there. But that's something that's often used in the literature. And I'll skip this. Will did that test for these compounds here too. It turns out for band structures this works well up to about cadmium, and still not too badly up to the elements up to gold, really. Only in the 6p shell it's known that this approximation that I just showed, but just retroactively introducing this spin-orbit coupling operator breaks down. It doesn't break down terribly much, in fact. If one looks at band structures of something like bismuth, one sees that the scalar relativistic band structure, for instance, looks like this. It has levels here that are at the same place. Over here, a gap has opened up that's several electron volts large. And so if you treat this correctly, including a spin-orbit coupling operator, even in different versions, you see that basically those different approximations give the qualitative physics correctly up to a few percent compared to the scalar relativistic solution, which would simply be wrong for the band structure. All right, Carsten reminds me that it's minus 5 minutes. I would have talked about eigenvalue solvers. I'll just say that if you have an eigenvalue solver that's really good and you have a large computer, so 10 to the 5 CPUs or so, you can diagonalize a problem that has maybe 1 million basis functions. So this is a data point done by Alvaro Vasquez in Aragon using the ALPA eigensolver. That's done very good things for us in FHI-AIM. So this is at the heart of scalability of the code. Victor Yu, who's in the audience, is working on a method of integrating other solvers, so solvers that also go beyond order n cubed in a single framework that we call LC, so that basically connects different DFT codes. So this is an open source library to different types of solvers. If an eigenvalue solver is your best bet for small systems, we can do that, but in principle we should be able to go to larger systems seamlessly by switching to other solvers, and this is what this library is going to do. This is actually something that works. So the red line here is order n cubed for a graphene sheet, a set of graphene sheets that becomes progressively larger. At some point you can switch over to a method that here scales order n to the 1.5, which is called PEXI, and I think Lin Lin, who's going to be here later, will talk about this in more detail. I'll wrap up by saying that this thing here is paradigmatic of things that are going on in the community overall. So this here is a library that can connect to FHI-AIMS, but it can connect to other things as well, like the ALPA library. There's an effort going on called the SICAM electronic structure library that's collecting such libraries and trying to put them into a sort of coherent organization and also develop them further. And ultimately, I think as a bundle that one can link against with an electronic structure code without having to program, say, the exchange correlation functional oneself. So this is a very useful idea to go from here, different codes that are all separate, to this kind of version where the libraries are basically shared as needed between different codes. So from a code development point of view, that's, I think, where a lot of work is going to happen in the next few years. I'll thank you for your attention. This is the summary. These are part of the concepts I try to talk about today. More technical concepts will follow tomorrow by Oliver Hofmann. Thank you very much.